Hi everyone, this is a tutorial video to look over calculating the pH of solutions that contain the conjugate base of a weak acid. We've seen that conjugate bases of weak acids can behave as bases in water and actually make the pH greater than 7, which is somewhat unexpected, but is the case in nature. So we're going to work through a problem using a rice table. Calculate the pH of a 0.5 molar solution of sodium carbonate. The Ka of HCO3 minus is 5.6 times 10 to the minus 11. Now before we can set up a rice table, we need the R, which is reaction. So we've got to write a reaction equation for this. Remember, sodium is going to be a spectator. We're going to completely ignore it. So we're just going to start with the carbonate. Just going to start with the carbonate ion and ask ourselves, how would that behave towards water? We've been given a hint in the problem because we're told that the Ka of HCO3 minus is this value. So we know that the conjugate acid we're going for, or rather the acid for which this is the conjugate base, is going to be HCO3 minus. And in order for the CO3 minus to have picked up an H, it must have gained that H plus from the water, leaving behind hydroxide, OH minus. Be careful here with your charges. It's easy to forget to do the charges here. Notice that the carbonate went from 2 minus up to 1 minus because it gained an H plus ion. The water goes down from 0 to 1 minus because it's lost an H plus ion. All right, so now we have a reaction. So now we're going to set up a rice table. Initial change equilibrium. The only thing we're given is that the initial concentration of the carbonate solution is 0.5 molar. So we're going to put 0.500 here. We don't have to worry about the water because it's a liquid. Its concentration won't change. It has an effective concentration of 1 by convention. So we're just going to put a little squiggle through that to remind ourselves. There's none of these given to us as initially present. So we're going to assume that they're 0. So the reaction has to proceed in the forward direction to create some products. So we're going to do minus x plus x plus x. All the coefficients are 1. So these are minus x plus x plus x. At equilibrium, we just add up the initial plus the change. All right, and now we're ready to go. Except for one problem. We don't have the Kb for this. Remember that anytime we see hydroxide on the product side, that we're going to be using a Kb. So how do we do that? Well, we're given the Ka of the conjugate. Remember that we have this equation. The Ka times Kb is equal to Kw. Let's remember, Ka is the equilibrium constant for the acid. Kb is the equilibrium constant for the conjugate base of the acid. Kw is this constant that we use that's temperature dependent. Because the problem didn't say so, we're going to assume that this is happening at 25 Celsius. And therefore, we can use our most familiar form of Kw, which is 1.0 times 10 to the minus 14. So now we're going to plug numbers in here. And we know that the Ka is 5.6 times 10 to the minus 11. We don't know the value of Kb yet. Kw is 1.0 times 10 to the minus 14. So we divide both sides by 5.6 times 10 to the minus 11. And then we go looking for our calculator because we forgot to bring it. Okay, sorry for that. So now on my TI-83, we're going to do this as 1e minus 14 divided by 5.6 e minus 11. Depending on your calculator, you may have to enter this in a different way. So now we're going to get a value of we're going to call it 8 because of significant digits. We have a Kb value of 1.8 times 10 to the minus 4. Now we're ready to go and solve the problem. So we know that the Kb for this reaction up here is going to be products over reactants. And I know sometimes you guys are trying to rush, but I really encourage you to actually write the KB expression, even if it's not explicitly asked for in the problem. All right, so these two are x, and that's going to be over 0.5 minus x. So 1.8 times 10 to the minus 4 equals x squared over 0.50 minus x. We're going to neglect that x because we know that it's going to come out to be too small to change the answer for the problem. So when we plug all this in, we're going to get that x is equal to that value of our KB times 0.5 and then the square root of that. Okay, so x comes out to be 0.0094. And the question we were actually asked for way back here at the beginning was to actually calculate the pH. Well, our x here is actually our hydroxide concentration. So if we take the negative log of that, that's going to give us the pOH. Negative log of our answer. And that's going to be 2.0 is our pOH. Because again, we're at 14, we can subtract, we're at 25 Celsius, we can subtract that from 14 and get that our pH is going to be 14 minus 2.0, which is going to be 12.0. And that's how we solve the problem of the pH of a ionic compound that contains the conjugate base of a weak acid.